Alright, welcome everyone to our first video lecture. So we're going to be moving into chapter 8 today, so talking about applications of integration. So if you don't already, go ahead and get those guided notes out. They're posted on the Canvas page, so if you're going to use your technology, or if you're going to print them out and write on them, or you're just kind of following along as we go here, we are going to be using those guided notes throughout the chapter, so make sure you have those ready to go. So in section 8.1, we're going to be talking about the concept of arc length and how we can find the length of an arc of a curve using integration. So to start off here, I'm just going to put a curve up here that we can work with. Something like that. We're going to put some points on this curve. So it doesn't have to be perfect, but then I'm going to identify the x-coordinates at each of these points. And they should be relatively evenly spaced, right, as close as we can get. Okay. So on the interval, we're going from A to B, and then each of these points in between, we're going to start labeling like x1, x2, x3, etc., etc. And then in the middle here, we're going to have x sub I minus 1, and then x sub I. And these are just arbitrary, so they could occur anywhere. It's just a labeling thing. X sub I. And then that continues onward there. And then the points on the curve, we're going to identify as starting at P naught, right, P1, P2, etc. Right, we have P sub I minus 1, P sub I, all the way up to P sub n. Okay, these are all points on the curve y equals f of x. Okay, so that's the curve that we're working with here. Now, if we're trying to identify the length of any one of these segments, so any section of this curve, that's what arc length gives us. It gives us the length of any strip on this curve. And in order to compute that, well, for now, we're just looking at an approximation. So we're going to approximate this using polygons. So for a polygon, we're just basically going to be connecting these dots. So instead of saying, I'm going to look at the exact length, I say, well, I'm going to create a straight line that's going to relatively approximate the value of this curve. So you can see, just by using those polygon approximations, we don't get the exact length of the curve, but it would give us something that might be close enough. So if we're looking at any one curve in particular, so I'm just going to focus in on the one part of the curve from P sub I minus 1 to P sub I. So it looks kind of like that. So here's P sub I minus 1 to P sub I. When we draw our polygons, okay, so we basically are just connecting these 2 points via straight line segment. Now, when we're looking at defining the arc length, well, that comes to this formula down here. Okay. So we're looking at the limit as n approaches infinity of I going from 1 to n, the sum of the length from p sub I minus 1 to p sub I. So just break this up into its components. So we're taking the distance, the length between each pair of points. Okay, so that's this arc length, that's the polygon, the straight line. We're adding up all of those lengths. And then here's where the limit comes in. The limit, as n approaches infinity, says that as we start taking more and more approximations, our value is going to get closer and closer to the actual length of the curve, or the length of the arc, right? So on our curve, if we go ahead and just take, let me put a couple more down here, just for reference. If we go ahead and we use more subdivisions, so instead of going straight from here to here, instead of it just being one approximation, we make it 2. Already, you can tell that this is going to be a better approximation than just having 1. If we break this into a few different pieces, so I divide it a couple of times, you get that to there, to there, right? So n tells us as the number of approximations increases, right? The number of points that we use for our estimates increases towards infinity. The value of these approximations gets closer and closer to the actual length of the curve, right? And if I even split it even more so, do it 1, 2, 3 points in here, get 1, 2, 3, 4, right? And we're almost on top of it at this point. So you can see our approximations do keep getting better and better as we go. Right? Now, this is similarly to how we've done, integration and derivatives and all that stuff in the past. We derive the formula here that we look at analytically. However, that's not the one we want to use when we're actually computing arc length. So we can derive a more friendly formula for arc length that incorporates the concept of an integral. So we say that if f prime is continuous on the closed interval from a to b, then the length of the curve, y equals f of x, between a and b is the following. It is L equals the integral from a to b of the square root of 1 plus f prime of x squared dx. So this is our formula for arc length. Okay, so this is the one we're going to be using when we're trying to compute the exact length of a curve. Okay. Now, oftentimes you'll see it is useful for us to write this in Leibniz notation. It doesn't change anything about how we solve this. We're just going to put it in slightly different notation. So instead of f prime of x, we're going to use dy dx squared dx. Because oftentimes we're going to be working with different variables. So sometimes we'll work in terms of x, sometimes we work in terms of y. So this makes it a little easier to identify the variables that we're working with, both input and output. So let's look at this example. So find the length of the arc of the function y squared equals x cubed between the points 1, 1 and 4, 8. So let's go ahead and take a look on Desmos. Let's see what this curve actually looks like. So we have y squared equals x cubed and we're looking at the portion of this curve from the point 1, 1 to the point 4, 8. So that's going to be right there. Okay, so and I can actually put a little bit of a restriction on this. So if I get y squared equals x cubed, and then I just say I want x between 1 and 4. There we go. Then you can see this is the portion of the graph that we're looking at. We're trying to find the length of this curve. Okay. So, when we're working with this curve, it's going to be easiest for us to probably put this just y in terms of x, like we're typically used to working with functions. So, when we're on the top half, so when we're on the top half of the curve, we have y equals x cubed, right? Take the square root, so that's x to the 3/2 power. So if we're trying to take a derivative of this, we just use the power rule. So dy dx equals 3/2 x to the 1/2. And that would be our derivative. So the arc length would be L equals integral from 1 to 4 of the square root of 1 plus 3/2 x to the 1/2 squared dx. Okay, and then go ahead and simplify that square inside the root. So that's going to be square root of 1 plus 9/4. X to the 1/2, that's the square root squared. That's just x. So 9/4 x dx. Now, in order to solve this, we're going to need to, of course, take an antiderivative. To do that, I'm going to do a u sub. So I'm going to let u equal 1 plus 9/4 x, and then du is just 9/4 dx. Right? So dx is 4/9 du. Okay, that'll help us set up our integral in terms of u. We're also going to need to convert the bounds as well. Okay, I guess we don't necessarily have to, but I will. Just one less thing we have to do later. So, some more room here. So for our bounds, when x is 1, using our u substitution, u is 1 plus 9/4. So that's like 4/4 plus 9/4. So that's 13/4. And when x is the upper bound, when x is 4, u is 1 plus 9/4 times 4. The 4's cancel, that's just 1 plus 9, which is 10. So, our u substitution, we have the integral from 13/4 to 10 of the square root of u times 4/9 du. So we get, so the 4/9 just a constant multiple, so that's out there. 4/9 times the antiderivative of the square root function, so you're undoing the power rule, but that's 2/3 u to the 3/2, and that's being evaluated from 13/4 to 10. So we have, 4/9 times 2/3, that's 8/27 times 10 to the 3/2 minus 13/4 to the 3/2. And then we can simplify that a little bit, put it back in the root notation. So we're going to get, if we multiply the 8 in, I'm going to leave the 1/27 out here. This ends up giving us 80 root 10 minus 13 root 13. Okay, so there's a little more simplification that goes into that, but it's just a little bit of algebra playing around with the exponents and converting them back into roots again. Okay. So this value, this gives us the length of the arc on the curve y squared equals x cubed between the points 1, 1 and 4, 8. Okay, so that would be this value. Now, we also can define curves in terms of y, not just in terms of x. And this is where sometimes our Leibniz notation can come in handy a little bit. So if we want to define arc length of a curve in terms of y, then we would write, this is the integral from c to d of the square root of 1 plus, so using the prime notation, it would be g prime of y squared dy. And then using Leibniz notation from c to d, we have square root of 1 plus, this would be dx dy, so derivative of x with respect to y squared dy. That would be our formula for arc length for a function with respect to y instead of with respect to x. So for this example, find the length of the arc of the parabola y squared equals x from 0, 0 to 1, 1. Okay, so this is the sideways opening parabola, right? So we have x equals y squared. So let's just do this one in terms of y. So dx dy is just going to be 2y. So L, our arc length, is going to be integral from 0 to 1 of the square root of 1 plus the derivative squared. So that would be 4y squared dy. Now, in order to solve this integral, we're going to have to use one of our techniques of integration that we saw in the previous chapter. This one does fit one of those styles, so think about which one you might use here. But I can tell you, we are going to be using a trig sub in this case. So the square root should hopefully kind of give that away a little bit. So we are going to do a trig sub. Okay. And the trig sub that we're going to choose is going to be y equals 1/2 tangent of theta. So that's the trig sub that we're going to be using here. Then dy, in this case, would be 1/2 secant squared theta, d theta. So when we're trying to do the substitution, So the square root of 1 plus 4y squared. That's going to be square root of 1 plus, well, 1/2 squared is 1/4. So the 4's will cancel, and we'll just be left with tangent squared theta. And 1 plus tangent squared is secant squared, and then the square root of that is just secant of theta. Okay, so that means our formula here, we have the integral. I'm going to ignore the bounds for a second because we're converting to theta right now. So we'll come back to that in a moment. This is the integral of secant of theta times 1/2 secant squared theta d theta, right? That was dy. So this gives us 1/2 times the integral of secant cubed theta d theta. And this integral, we've actually done this one before. So this integral was in section 7.2. So if you go back into that section, you'll see that we have solved this one before. So I'm just going to cut kind of to the chase on this one. The value of this integral, so we would get 1/2 times, it ends up being times another factor of 1/2 because of the solution, times secant theta tangent theta plus ln of the absolute value of secant theta plus tangent theta Now we need to substitute back in terms of y so that we can solve this using our original bounds. So in order to do that, we are going to set up a triangle like we did before in some of our previous examples. So here's our triangle. So let's think about what we know about tangent. So we know that y equals 1/2 tangent theta. So that means tangent theta equals 2y over 1. So here's our angle theta. So tangent is opposite over adjacent. So that's 2y and 1 right there. So secant theta, that's going to be 1 over cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. And the hypotenuse, using the Pythagorean theorem, that's going to be square root of 1 plus 4y squared. So secant is just going to be square root 1 plus 4y squared over 1, but we don't need to write over 1. And this is going to give us all the pieces that we need. So this is 1/4 secant theta, tangent theta. So tangent theta is 2y. Secant theta is the square root. So this is 2y times the square root of 1 plus 4y squared. And then plus ln of the absolute value of secant theta, so that's square root 1 plus 4y squared, plus tangent theta, so plus 2y. And now that we're back in terms of y, we can evaluate back at these original bounds that we started with. So that's going to be from 0 to 1. And if you go ahead, evaluate those bounds using fundamental theorem of calculus, you will get, when all is said and done, we get root 5 over 2 plus ln of root 5 plus 2 over 4. And that would be our arc length. That's the length of that parabola, y squared equals x, from 0, 0 to 1, 1. Okay, so again, the only really new thing here that we've done in these problems is the setup. So it's this part right here. That's really the only new thing that we've done. Everything else was from chapter 7. So this is why those techniques of integration are important, because we need to be able to use them and apply them for other contexts as well. So that brings us to the arc length function. Now the arc length function, this allows us to, similar to a derivative function, allows us to compute the derivative at any point on a curve. The arc length function allows us to find the arc length from a specified point A to any value above it. Okay, so instead of saying I'm going specifically from A to B, I say, well, I'm going to go from A to X, and X can just change, and we can make X whatever we want it to be. So this can be very useful in determining formulas for arc length for any given curve. So the function for arc length, this is going to be written s of x, and that's equal to the integral from A to X of the square root of 1 plus f prime of t squared dt. And if you're wondering, wait a second, why is there a t in here? T is just a placeholder variable. It really doesn't matter. It's just that we don't want to use x in the bounds and use x on the inside because that can get confusing. So, but if we apply the fundamental theorem of calculus to this, part 1, and we take the derivative of both sides, we get ds dx, right? So the derivative of s with respect to x equals just the square root of 1 plus f prime of x squared. Right, and that's what part 1 of the FTC says. If you take the derivative of an integral, you get out just the original function. Now when you write this as a differential, okay, so taking ds and dx and separating them, we get ds equals the square root of 1 plus f prime of x squared dx. And this is equivalent to our very first definition for arc length. So if we go back and look way back at the beginning, right here, if you were to take the integral of both sides of this differential, you would get integral from a to b of the square root 1 plus f prime of x squared dx, and that would be the integral of this, right? So if we did, right, integral of this, right, that would give us our arc length formula. So symbolically, it often gets written as the integral of ds, but really we're just talking about this expression right here. Okay, so let's look at one more example, now dealing with this arc length function instead of a specified arc length. So find the arc length function for the curve y equals x squared minus 1/8 ln of x, taking 1, 1 as the starting point. So first thing we need is the derivative, always a good first step. So f prime of x equals 2x minus 1 over 8x, right? Derivative of ln of x being 1 over x. So then for our formula, so 1 plus f prime of x squared, that's going to be 1 plus 2x minus 1 over 8x squared and then if we FOIL that out, we get 1 plus 4x squared minus 1/2 plus 1 over 64x squared. Combine the 1 minus 1/2. That's just going to give you plus 1/2. And that, believe it or not, is actually factorable. So it's similar to this one, how it was factorable. So this ends up giving us 2x plus 1 over 8x squared. So our formula for the square root of 1 plus f prime of x squared is the square root of 2x plus 1 over 8x squared. So it's just 2x plus 1 over 8x. Of course, the square and the square root canceling each other out. So our formula, so s of x, that's going to be the integral. 1 is the starting point, so from 1 to x, of 2t plus 1 over 8t dt, again using t as our placeholder variable. Take the antiderivative of this, that's t squared plus 1/8 ln absolute value of t, evaluated from 1 to x. We won't need to keep the absolute value on that ln just because we know that all the values are going to be bigger than 1. So evaluate, you get 1 squared, start with the x. We get x squared plus 1/8 ln of x minus 1 squared plus 1/8 ln of 1. ln of 1 is just 0. So we end up getting x squared plus 1/8 ln of x. 1/8 ln of x minus 1. And that is our formula for arc length for this function. Okay. So what we could do once we have this formula, so we could just for example, if we wanted arc length from 1, 1 to 3, comma, whatever the output is, 3, comma f of 3. All we would need to do is plug in 3. So s of 3 would be 3 squared plus 1/8 ln of 3 minus 1, which if we were to use technology, we would get this as approximately 8.1373. But we would get this value, and that would tell us the arc length starting at 1, 1, always, going up to 3, comma f of 3. We could do this from 1, 1 to really any point along this curve, and if we wanted to do it for any other starting point, then that just changes how we evaluate the integral. Just pick different bounds to start. Okay. So this formula for the arc length allows us to get arc length from a specific starting point to any value on the curve that we want. All right, and that is section 8.1. So that's the end of our topic about arc length. We will be seeing it come up in the next section as well, but we'll get to that when we start section 8.2.